Welcome back, dear students. This is the second part of the Unit 3 that we state statistical correlation and regression. This unit is focused on the introductory part of the term regression. So, we shall see what regression is and some theoretical aspects of certain properties in this particular video. So, let's begin. We first begin with the definition of regression, then discuss certain types, and then lines of regression. So, what are the various variables we will be talking about in regression? And based on which, what do we mean by regression lines or regression equations? Just like how we derived correlation is a measure of the relationship between any two variables, regression is the study of the relationship between variables. So through regression, we can develop what is the relationship between variables, whereas correlation told us how closely were the variables related. So regression is the study of what is that relationship that relates the two variables. So it's a study of these, and hence we derive certain equations in regression for which we require certain variables. So what are the two types of variables that we study in regression? One is an independent variable and the other is a dependent variable. As the name goes, the independent variable is that variable whose value influences the other values, or is used for prediction. So normally when we talk about independent variable, we in our general mathematics, we represent x to be the independent variable and y to be dependent on x. So this independent variable x either has its own value and it is used to predict the value of the predictor, meaning the value of the dependent variable. So as the word suggests, x is the independent variable, y is the dependent variable. This is by default that we choose, but it could also be the other way around. So an independent variable is one whose value influences the other values or is used for prediction. And a dependent variable is that value which is getting influenced. Here it is y in my example that I take. If I have x to be a function of y, in this case x will be dependent on y and y is the independent variable. So a dependent variable is that one which whose value is either influenced or is to be predicted. For in this example it is y and in this example it is x. So these are the names given for those kind of variables, which are also called regressor in the case of an independent variable, or a predictor, or an explanator. These are the synonyms of independent variable, whereas the synonyms of dependent variable are regressed or explained. Using these variables, we can derive two lines of regression. So the first line of regression we are talking about is the regression line of y on x. That means if y is treated to be the dependent variable and x is the independent variable, then the linear relationship that we can develop between x and y is called the regression line of y on x. And it is given by y minus y bar is equal to rho times sigma y by sigma x into x minus x bar. By looking literally at the equation, we can easily state that it's of the form y equal to mx. Here our y bar and x bar represent the mean of x and y. Rho represents the correlation coefficient between x and y. Sigma x and sigma y represents the standard deviations of x and y. So making use of these, we can construct the equation which is called regression line of y on x. This is one of the lines of y on x and is used for a particular case alone, which we shall discuss in our next slide. So I'm sure you can guess what is the next line. If this was called regression line of y on x, the second line is called regression line of x on y, about which we will discuss in our next slide. So as you rightly guessed, the second line of regression is called the regression line of x on y. So, and that is given by x minus x bar equal to rho times sigma x by sigma y into y minus y bar, where all of them mean the same. X bar, y bar denote the means of x and y respectively. Rho is the correlation coefficient between x and y. Sigma x and sigma y both represent the standard deviations of x and y respectively. Kindly note here that when you wrote the regression line of y on x, it was of the form y minus y bar equal to rho times sigma y by sigma x. That's where the difference comes. When you're writing it as y on x, the numerator is sigma y, the denominator is sigma x, the left hand side is y, the right hand side is x. And when you wrote the regression line of x on y, you have x on the left side, x on y, the x on the left side, then you have rho times sigma x in the numerator, sigma y in the denominator, multiplied by y minus y bar. So this is the difference. In y on x, you have sigma y by sigma x form, and on x on y, you have sigma x by sigma y form. And here you have x occurring on the left side, y occurring on the right side. Both represent equations of the form y equal to mx. Now you must be wondering, why do we have to derive two linear relationships like this? Both have a different basis. Since we are not dwelling into the derivation here, we must understand that the assumptions and the basis of deriving the two equations are very different, meaning that in the first case we had x to be the independent variable, whereas in the second case we have x to be the dependent variable. And why do we use, where do we use these two lines? What are the two lines used for? They look to be linear, but yet we are using it for two different purposes. That is, the regression line of y on x, when we treated y to be a dependent variable on the variable x, this line is used to estimate the value of y when you are given the value of x. So regression line of y on x is used to find the value of y when you're given the value of x, whereas the regression line of x on y is used to find the value of x when you are given the value of y. So we are not going to use it interchangeably. That's one of the main properties of regression. We have two different lines for two different purposes. So the dependent variable, if y is the dependent variable, we are using regression line of y on x to obtain its value. And if x is the dependent variable, we are using regression line of x on y to estimate its value. So the two lines are required for two different purposes, and the same linear equation cannot be used because the error that is involved, in case we do that, in case we do it, the error that is involved is maximum, and we would like always to minimize the possible error, and hence the need of two regression lines instead of one. Let's proceed further. As we have learned that the two lines take up the form y is equal to mx. If you look at the standard equation, m is called the slope of a line. So in our case, the slope of the regression line of y on x will automatically be rho times sigma y by sigma x, and the slope of the regression line of x on y will be automatically rho times sigma x by sigma y. So this is given a special name called regression coefficient of y on x. So the slope of the regression line of y on x is denoted by byx. So that's how I write here. It is defined by rho times sigma y by sigma x, and it is denoted by a formula which is similar, I don't, it's not exact, but similar to the formula of rho. How is it similar? I say, look at the numerator. It is n times sigma xy minus sigma x into sigma y. So don't you see it's the same for your direct method that you did? And the denominator without a root contains only x term because you have denominator as sigma x. So it is n times sigma x square minus sigma x the whole square. So this is the notation for the regression coefficient of y on x, which is denoted by byx and given by rho sigma y by sigma x. So in problems, we use this formula in order to find the value of byx when the standard deviations are not given directly. The similar way, the slope of regression line of x on y is denoted by bxy, that is this, and it is defined by rho times sigma x by sigma y. And as you can see, the numerator is the same, but denominator, since you have sigma y here, the denominator will be a function of y. So it's n sigma y square minus sigma y the whole square. So we shall use these formulae in order to calculate regression coefficients. So we have now learned what is regression, what are the variables that are used in regression, and basing on which what are the lines of regression, and using the lines, from the lines we declare the slopes of these two lines to be called as regression coefficients of y on x and x on y. Now we shall end this particular theoretical part by declaring certain properties of regression coefficients. You have seen in the previous slide that the two lines are of the form y minus y bar equal to rho times sigma y by sigma x into x minus x bar, and the other is x minus x bar is equal to rho times sigma x by sigma y into y minus y bar. So you note here that the two lines will pass through the point x bar y bar. So that means the two lines, when they pass through x bar y bar, we can declare that x bar comma y bar is the point of intersection of the two lines. So the regression line of y on x passes through x bar y bar. Regression line of x on y also passes through x bar y bar, and therefore we can declare that the point of intersection of the two lines is the point x bar y bar, which is the coordinate of means. The second one, the two lines are not reversible or interchangeable. As I told you, we are not going to use an equation for a different purpose. So each line has a particular purpose because the basis and assumptions for deriving these lines are different. Now you may say that I can find the value of y when I know the value of x. That's why this regression line of y on x is used for. Can I also use it to predict the value of x when I know y? The answer is no. So these are not reversible or interchangeable. So the regression line of y on x has a particular purpose of finding only the value of y when you know x. And regression line of x on y has the only job of finding the value of x when you have the value of y, because the basic assumptions itself are quite different. In case of perfect correlation, when do you say correlation is perfect? When rho is plus or minus 1. So when it's either plus 1, you say it is perfectly positive. When it is minus 1, you say it is perfectly negative. In such a case, what will happen if you look at this? This becomes, you change it as minus 1 or plus 1, you remove the row here, you remove the row. Will you find that the two equations coincide? Y minus y bar will become equal to sigma y by sigma x or minus times it. So this is the only case where the two equations will coincide and become the same equation. So only in the case of perfect correlation, we will have only one line. In all other cases, we can derive two lines. Then the correlation coefficient is a geometric mean between the regression coefficients. If you note, the geometric mean between two numbers a and b is plus or minus root ab. So that's how it is defined. If we can recall, let's see how do we declare that here? Geometric mean between the regression coefficients, I say. So I multiply the two coefficients. I get rho times sigma x by sigma y as bxy, rho times sigma y by sigma x into bxy. Now what do you see? You see sigma y cancelling out, sigma x cancelling out, giving you rho square, and taking the square root, it becomes plus or minus root of the product of the coefficients. So correct. Correlation coefficient is represented as the geometric mean between the regression coefficients. Perfect. Now, coming to the sign, we said rho equal to plus or minus. What would be the sign of rho? Naturally, you would all know that bxy now contains rho sigma x sigma y. Byx also contains rho, sigma y, sigma x. It's only the position of sigma x and sigma y that changes, but the terms that are used to obtain the values are the same. And therefore, either both bxy and byx will be positive or both will be negative. So we decide the sign of rho based on the sign of bxy and byx. If both are positive, then rho is positive. But if both are negative, then we take rho to be negative. So this plus or minus can be segregated that way depending on the sign of the coefficients. Then, if one of the regression coefficients is greater than unity, then the other will always be less than unity. That is obvious from the rho square that we take, as we say that rho square is always less than or equal to 1. See, you see, rho square is always less than or equal to 1. That means bxy into byx is always less than or equal to 1, or I say bxy is less than or equal to 1 by byx. So naturally, when one is less than unity, the other must be greater than unity. And regression coefficients are independent of change of origin and scale. So we studied this when we tried to use the assumed mean method by treating our x to be small x. If I want to take some other variable as x minus a by h, I want to change it and write it as dx. We are changing it by subtracting a and we are dividing it by the scaling factor. So here also you can do, instead of using the direct method, you can use the assumed mean method in order to declare your values. So in that case, regression coefficients can be found even in an easier manner. Instead of using capital X and Y, we shall use dx and dy as we did in the case of correlation. So these are the basics that we have learned. This is the basic introduction of regression. Now we shall take this introduction into our problems and attempt a few problems in our next video. So for now we shall stop it here. Kindly go through all the slides, understand the concept, so that in the next video we can attempt doing some important problems. Thank you for being there and being patient. We shall meet again in our next video.